right? So I told you, Pute, I am going to discuss all the chemistry practicals in grade 10 today, right? Then we can complete the chemistry session in grade 10, right? So here, first I hope to discuss about the gas preparation, right? There, when we discuss about the gas preparation, we have to know the properties of the gases. Here, properties means both the physical properties and the chemical properties, Pute, right? And also how we can prepare the gases and how we can identify those gases and what are the uses of these gases and also the collecting method of these gases, right? So today, first we discuss about the gas preparation. Right? So under the gas preparation, Pute, right, only we have to know about three gases, right? What are those three gases? Hydrogen, carbon dioxide and oxygen, right? Only about these three. Right? So hydrogen, carbon dioxide and oxygen gas, right? We will go through the theory part, right? When we consider the hydrogen gas, right, we know that it is less denser than air, right? And when we consider the percentage of the atmosphere, right, hydrogen gas is only a very small percentage, right? So then as I told you, we have to know the physical properties and the chemical properties of these gases, right? So the hydrogen is a gas with a less density than the normal air. And the relative molecular mass is 2, 1 plus 1. Relative molecular mass 2, right? And you have to know, Pute, those two, right? And it is a combustible gas, right? Combustible gas. Don't mix the supporter for the combustion and the combustible gas for the, right? Supporter for the combustion means, right, for the combustion that gas is needed. That is why we consider it as a supporter for the combustion. But here, hydrogen is a combustible gas, Pute, right? Combustible gas. That means it can burn, right? Hydrogen is slightly soluble in water and it is colorless, odorless. No color, no smell, right? And the method that we use to prepare the hydrogen gas, right? This is a normal method that we use in the lab, right? We get the reaction between zinc and hydrochloric acid, right? Pute, zinc and hydrochloric acid, right? And you have to go through or you have to familiar with this experimental setup, right? Experimental setup. For the conical flask, right? We put some zinc granule or small pieces of zinc, right? Small pieces of zinc, and using the Tissot funnel here, from here, right, we put the hydrochloric acid, right? And through the delivery tube, we collect the hydrogen gas, right? We collect the hydrogen gas here, right? And the collecting method we use, right? For the gas jar, right, I am drawing only that part, Pute, here. Right, the collecting method. Right, this is the trough, and here we use the gas jar. Right, we connect the delivery tube here. I'm drawing only the one part of the experimental setup, Pute, right? So we have to fill water up to this level, right? And at the beginning of the experiment, right? At the beginning of the experiment, Pute, the gas jar is completely filled with water, right? Completely filled with water, right? When the reaction is going on inside the conical flask, the reaction between zinc and hydrochloric acid, what happens, Pute? Hydrogen gas is produced, right? So that hydrogen gas sent through the delivery tube, right? That hydrogen gas sent through the delivery tube to the gas jar, right? Then what happens? We know that gas is a matter, right? It has a mass and it occupies space, right? So what happens here is when the hydrogen gas enter to the gas jar, what will happen, right? That air needs space. or the air occupies space inside the gas jar, Pute, then we can observe the water level in the gas jar, right, goes down, right? The water level in the gas jar goes down, right? Water goes down. So we name this method the collecting method of hydrogen gas, that is what? This one, downward displacement. Right? Downward displacement of water, right? Because the water goes down when the hydrogen gas enter to the gas jar, right? In here, at the upper level of the gas jar, hydrogen gas fill here, right? So the water goes down. That is why we name this method downward displacement of water, right, Pute? Downward displacement of water, right? So that is the collecting method of hydrogen gas, right? And there is another method of collecting hydrogen gas, right? What is that? At the beginning, I told you when we consider the properties of hydrogen gas, it is less denser than air. If it is less denser than air, it goes up in the atmosphere, right? Not down, it goes up because it is less denser than air. So, to an empty gas jar, we can collect hydrogen gas by this method also, right? So, here we have to enter the delivery tube to an empty gas jar like this. Empty means inside the gas jar there is air, right? So what happens when hydrogen enter to the gas jar, right? The air goes down, Pute. Air goes down, right? Atmospheric air goes down, right? So we name this method downward displacement of what? Air, right? Downward displacement of air, right? So by this method also we can collect hydrogen gas, right? So the property we use here is because hydrogen is less denser than air, right? So we use that property to use this method to collect hydrogen gas, right? So there are two methods that we can use to collect hydrogen gas, right? And here you are given the uses, Pute, right? It is used as a fuel in rockets. Fuel, I told you, it is a combustible gas, right? It burns and it gives energy, right? So it used as a fuel in rockets, right? And in the production of margarine and production of ammonia gas, ammonia, NH3, right? By the combination of nitrogen and hydrogen gas, ammonia gas is produced, right? And in the reduction of organic compounds, right? So those are the uses of hydrogen gas, right? Then we comes to the oxygen, right? It is a very familiar one, right? You know the percentage of what the atmosphere, right? It is nearly 21%, or we can say 1/5 part of the atmosphere, right? So here also we have to know the physical and chemical properties, Pute, right? The density is lighter than that of normal air, right? It is also less denser than air, right? And the relative molecular mass is 32, 16 plus 16, 32. Relative molecular mass of oxygen gas, right? And I told you, it is a supporter for combustion, Pute. It is a supporter for combustion. That means we know for the combustion, there are the three factors should be fulfilled. There should be a combustible substance and there should be a supporter for combustion. That means oxygen is needed for combustion and the combustible substance should be heated up to the ignition temperature, right? You have learned those things in the lower grades, right? So oxygen is a supporter for combustion, Pute, right? And it is slightly soluble in water. Slightly soluble in water. What is the importance of dissolving dissolving oxygen in water, right? Dissolving oxygen in water. It is important for the, yes, what? For the aquatic organisms, Pute. For the aquatic organisms, because they cannot use oxygen in the atmosphere for their respiration, right? They need this water soluble oxygen, right? So both the aquatic animals and plants, they need water soluble oxygen. So the solubility of water is important for the aquatic organisms, right? And also same as hydrogen, oxygen is colorless and odorless, right? Here you are given the methods that we can use to prepare oxygen gas, right? The most common one that we use in the lab is what? The first one, Pute, heating potassium permanganate, right? Heating potassium permanganate, and there are some other methods also, right? We can use heating potassium nitrate, or we can get the decomposition of hydrogen peroxide H2O2. That method also we can use, and heating potassium chlorate, right? We can use one of these methods, but the most common one is heating potassium permanganate. Here we use the boiling tube, right? To the boiling tube, we put some crystals of potassium permanganate, right? And by using the Bunsen burner, we have to heat it, right? Then here also, right, we use the same setup to collect the oxygen gas, Pute, right? The same setup here as we use in hydrogen, the collection of hydrogen, right? So here, through the delivery tube, oxygen gas is sent to the gas jar, right? Here also, when oxygen gas enter to the gas jar, the water level goes down, right? Water level goes down. So this one also, downward displacement of water, right? Downward displacement of water. That is the collecting method of oxygen gas, right? Then you are given the uses of oxygen gas, right? It is essential for the respiration of all the organisms, right? All plants and animals, right? Both of us need oxygen for the respiration, but for photosynthesis, right? That is a separate one. For the photosynthesis, plants use what? Carbon dioxide gas, and they release oxygen as a byproduct of photosynthesis, right? Now, when something burns, it reacts with oxygen, right? Burning means the combustible substances or the substance that burn, it reacts with oxygen, right? And so oxygen is essential for combustion, right? And it is used during the underwater diving and in space travel, right? It is used to generate the oxyacetylene flame, right? These are the uses, right? Oxygen is used as a raw material in industries such as the production of sulfuric acid and nitric acid, right? Sulfuric and nitric. So you have to remember these things, right? The uses of oxygen gas. Then we will move to the next one, carbon dioxide gas, right? I told you only we have these three, hydrogen, oxygen, and carbon dioxide, right? What are the properties of carbon dioxide? It is a gas with a density that higher than the normal layer, right? So carbon dioxide is higher denser than normal layer, right? The relative molecular mass is 44, and it neither burns or no supporter for combustion, right? It is not a combustible one, and it does not support for the combustion, right? And gas is slightly soluble in water, same as oxygen, and it is colorless and odorless, right? And the method that we can use to prepare carbon dioxide gas, right? We get the reaction between calcium carbonate and hydrochloric acid, Pute, right? Calcium carbonate and hydrochloric acid, right? Again, the experimental setup is same, right? Here, if it is in the lab, right? If we have calcium carbonate crystals, right? We can use calcium carbonate granules, right? You can ask that instead of calcium carbonate here, or if you don't have calcium carbonate in the school lab, what you can use, right, to prepare carbon dioxide gas, right? Yes, what are the things that you can supply from the environment, Pute? Yes, instead of calcium carbonate, yes, we can use eggshells, right? We can use eggshells, or the shell of the snails, right? Or, right, like that, we can use any calcium carbonate source to prepare carbon dioxide gas, right? If we don't have calcium carbonate in the school lab, right? So here also, we use the same method to collect carbon dioxide gas, right? When carbon dioxide enter to the gas jar, the water level goes down, right? Water level goes down and carbon dioxide enter to the gas jar, right? So the same method, downward displacement of water, right? Downward displacement of water. And there is a special thing here, Pute, that you have to remember. I told you, carbon dioxide is higher denser than air. If it is higher denser than air, that means in the normal atmosphere, it goes down because it is higher denser than air, right? So we can use this method to collect carbon dioxide gas, right? When carbon dioxide enter to the gas jar, right, the normal atmospheric air goes up, right, goes up. So we name this method as upward displacement of air, right, because air goes up and carbon dioxide goes down, right, because carbon dioxide is higher denser than air, right? So upward displacement of air because air goes up, right? Upward displacement of air, right? So for the three gases, right, hydrogen, carbon dioxide and oxygen, right, as a summary, Pute, right, we can use the method, as the collection method, we can use downward displacement of water, right, downward displacement of water. That is common to all the three gases, Pute, right? And for hydrogen, we can use what? The hydrogen is less denser than air, less denser than air. So it goes up, right? So for this one, we can use downward displacement of air, right? For carbon dioxide, it is higher denser than air, right? Higher denser than air. So we can use what? Upward displacement of water. Sorry, upward displacement of air. Right? Upward displacement of air. Right? So for hydrogen and carbon dioxide, there are two collecting methods. Right? And what are the uses of carbon dioxide? Right? Since carbon dioxide is a non-supporter for combustion, right? It used to extinguish fires. In the fire extinguishers, carbon dioxide is used, right? And
in extinguishers, what you have?
To form or to prepare carboxylic acid, right? Carbon dioxide is used, right? And carbon monoxide gas, right? It is a reductant for the extraction of iron, right? Is produced by the reacting carbon dioxide with coke, right? In between the reaction of carbon dioxide and coke, it forms carbon monoxide, right? In the production of iron, we use these reactions, right? So carbon dioxide is used to form carbon monoxide in the iron production, right? So those are the uses of carbon dioxide, right? Then the next one, how we can identify these three gases. It is very important. Yes, how we can identify these three gases, Pute, right? Hydrogen, oxygen and carbon dioxide, right? There is a unique method for these three gases that we can use to identify them, right? For hydrogen, right? When we collect the hydrogen to the gas jar, right? What we have to do is we introduce a glowing splinter or a burning flame, right? When we introduce a burning flame, what happens? It burns and with a pop sound, or the flame goes off with a pop sound, right? The flame goes with the pop sound. That is how we identify the hydrogen gas. When we introduce a burning flame, or we can say a glowing splinter, right? It goes off or it burns with giving a pop sound. That is how we identify hydrogen gas, right? Then for oxygen, there we use a glowing splinter, right? We use a glowing splinter. Right? When we use a glowing splinter, it burns with a bright flame. We can observe it burns with a bright flame, right? It burns with a bright flame. So we can confirm that is oxygen gas, right? We can observe the flame becomes bright than first, right? It burns with a bright flame, right? Then we can confirm the oxygen gas, right? Then for carbon dioxide, right, the normal identification method that we use, right? From grade 6 onwards, we learn this one. What is we use puthe, but colorless. Yes, we use colorless lime water, right? Colorless lime water. When we send carbon dioxide gas through a colorless lime water solution, what happens? This colorless lime water turns into milky, right? It turns into turns milky. So we can confirm that is carbon dioxide gas, right? So these three are the identification methods of these three gases, Pute, right? So you have to remember these, right? Then we will move to the other part, right? Can you see the screen? Can you see the screen, Pute? Yes. Right? Then we will go through the tune, right? Look at the first one, right? The first three questions are from the gas preparation, right? These are the practicals that related with the chemistry part in grade 10. So the most probably the third question in the structured paper, Pute, right? Third question is the chemistry one. So the third question of the structured paper most probably given by one of these practicals, right? Or otherwise from those graphs and or the periodic table. So we have to get ready, right? So we will move, right? Look at the first one, production of hydrogen gas, Pute. What is the method of collection of hydrogen gas? You are given a separate experimental setup. What is the collection method of hydrogen gas, right? According to this diagram, that is downward displacement of water, right? Downward displacement of water, right? What is the method of identification of hydrogen gas, right? We can use a burning flame, and the flame burns with a pop sound, right? The flame burns or it goes off with giving a pop sound. Then we can confirm that is hydrogen gas, right? Then what are the properties of this gas, right? It is not mentioned whether they have asked physical or chemical properties. So you can write any properties that related with the hydrogen gas, Pute, right? So it is less denser than air, it is a combustible gas, odorless, colorless, and the relative molecular mass is 2, like that you can write, right? Write down the balanced chemical equation for the production of hydrogen gas, right? Balanced chemical equation. What is the method we use? Right? So we discuss the method that producing hydrogen gas, the reaction between, yes, zinc and hydrochloric acid, Pute, right? So you can write that one, right? The reaction between zinc metal and the hydrochloric acid, right? Then it forms zinc chloride and hydrogen gas. Zinc chloride and hydrogen gas, right? Whether they have asked or not, when you write a chemical equation, you have to balance it, right? Otherwise, you cannot get the full marks for it, right? So we have to balance the chemical equation. I know that, I think that you know how to balance the chemical equation, right? We have to balance the two sides from the arrowhead, right? The atoms from the two sides of the arrowhead should be same when after balancing the equation, right? So in this side, only one zinc atom, and this side also only one zinc. That means zinc is balanced, right? Here, one hydrogen in this side, but here in this side, there are two hydrogen atoms, right? Here only one chlorine. In this side, there are two chlorine atoms are there, right? So we have to balance this side also, right? If we put 2 here, right now, 2 hydrogen, 2 chlorine in this side, and here also 2 chlorine, 2 hydrogen, that means the equation is balanced now, right? That is how we balance the equation. We cannot use fractions or decimals, only we use the whole numbers that is in front of the compound or the element or the metal, right? That is how we balance the chemical equations, right? So when you write the equations, whether they have asked or not, you have to write the balance equation, Pute, right? Then we will move to the second one, production of oxygen gas, right? The same things that we have discussed, Pute, right? What is the method of collection of oxygen gas, right? Here, according to the diagram, you are given that it is something, the heating of potassium permanganate, right? And the collection method is again downward displacement of water, right? What is the method of identification of the oxygen gas? When we introduce a glowing splinter, it burns with a bright flame, right? That is how we identify oxygen gas, right? Then what are the properties of this gas, right? The same properties we can write, and it is a supporter for combustion, right? It is a supporter for combustion. Relative molecular mass is 32, colorless, odorless, right? Like that you can write, right? Then write down the balanced chemical equation for the production of oxygen. Balanced chemical equation, right? We use the method heating potassium permanganate, right? Heating potassium permanganate. Potassium permanganate, KMnO4. Potassium permanganate, K valency 1, permanganate valency 1, KMnO4. I think you remember these things, right? So as the products, it form potassium manganate. Potassium manganate. K2MnO4, potassium manganate. Manganate, the valency 2, potassium 1. So the formula is K2MnO4, Pute, right? And it forms MnO2, manganese dioxide, and oxygen gas, right? The heating of potassium permanganate, right? To represent heating, we use a triangle like this, right? The balanced chemical equation. Look at here. There are 2 potassium here. Only 1 potassium in this side. 1 manganese here, and here 1, 2 manganese are there, right? In this side, 4 oxygen, right? All together in this side, 4 plus 2 plus 2, right? All together, 8 oxygen are there, right? So we have to balance the equation, Pute, right? So we put 2 here, right? At once you cannot balance these like this, right? You have to practice this one, right? Now 2 potassium, 2 potassium, 2 manganese, here also 2 manganese, all together 1 here, 1 here, and 4 into 2, right? 4 into 2, 8 oxygen, Pute, right? In this side also 4 plus 2 plus 2, all together 8 oxygen, right? You have to practice of balancing the chemical equations, right? Then look at the next one, production of carbon dioxide gas. What is the method of collection of carbon dioxide gas? Same as the 2 previous ones, downward displacement of water, right? What is the method of identification of carbon dioxide gas? When we send carbon dioxide gas through a colorless lime water, it turns into milky, right? Colorless lime water turns into milky. That is how we identify carbon dioxide gas, right? Why is that method used? Why is that method used? Because it gives a color change, right? It gives a color change. There should be a observable reaction, Pute, right, to identify a gas, right? So here, colorless lime water turns into milky, right? There is a color change. That is why we use this method. Then look at the fourth one. What are the properties of this gas? What are the properties of this gas? Right? It is also colorless, odorless, and it is not support for combustion, and it is not a combustible gas. Right? And you can write that one also. What? The relative molecular mass is 44. Right? Write down the balanced chemical equation for the production of carbon dioxide gas. Yes, what is the method we use here? The reaction between calcium carbonate and, yes, hydrochloric acid, Pute, right? The reaction between calcium carbonate and hydrochloric acid, right? So what are the products here? Calcium chloride, water, and carbon dioxide gas, right? Here also you have to check whether the equation is balanced, right? One calcium here, one carbon is there, right? And 3 oxygen here. Here also 2 plus 1, 3 oxygen, right? Here 1 hydrogen, right? But in this side, 2 hydrogen atoms are there, right? Here only 1 chlorine. In this side, 2 chlorine, right? So in this side also, there should be 2 hydrogen and 2 chlorine, Pute, right? Then very easy, we can put 2 here to balance the equation, right? So, right, you have to remember these 3, not only these 3, right? Normally for preparation of hydrogen and carbon dioxide, we use these 2 methods. And for oxygen, right, in the textbook, there are some other methods also given, right? So you have to go through them, Pute, right? Then we will move to the next one. This is a past paper question, right? From 2018, right? They have given a table, right, by covering all the 3 gases, right? It is somewhat different, right? Not given the diagram of the experimental setup, right? They make a separate table and answer some questions, Pute, right? Only we have to complete the table, right? Several observations and the test have done for you, right? Look at the first one, method of preparation, right? Method of preparation, right? There are some blanks. Adding drops of blank here onto solid manganese dioxide, right? And the remnants of the reaction mixture is given, right? What is remain after the reaction, right? Water is given. That means after the reaction, they say the water remain there. And a blank is there. That means another substance should be remain, right? And test to identify is given, inserting a glowing splinter, right? That is the hint that we are given, inserting a glowing splinter. And again, the observation also given, Pute, right? What is that? Rekindling of the splinter, right? Then very easily we can identify what is the gas, right? If we introduce a glowing splinter to identification, that should be, yes, what is the gas, Pute? Oxygen gas, right? So we can complete this blank here. The gas produced is oxygen, right? Gas produced is oxygen, right? Then look at the first 2 columns, Pute. The method of preparation and the remaining things, right? Normally, here also we discuss this method, right? Heating of potassium permanganate, right? It is not given here, right? Another method is given. Adding drops of blank onto the solid manganese dioxide, right? Manganese dioxide. So this method is connected with the reaction rate lesson, Pute. Right? In the reaction rate lesson, we discuss about a substance that can increase a reaction rate. Right? Those are called, we discuss in this one, right? In the TUD later, right? We name them as what? Catalysts. Right? So here, manganese dioxide is used as a catalyst. Right? So manganese dioxide is used as a catalyst in the reaction of what? Decomposition of hydrogen peroxide. Hydrogen peroxide. What is hydrogen peroxide? This one. Hydrogen peroxide, Pute. Right? Hydrogen peroxide. With the decomposition of hydrogen peroxide, it forms water and oxygen gas. Right? Water and oxygen gas, Pute. Right? So here they ask about this reaction, right? So in the decomposition of hydrogen dioxide, to increase the rate, we use manganese dioxide as a catalyst, right? Manganese dioxide, MnO2, right, Pute? We use manganese dioxide as a catalyst, right? So here, adding drops of, then we have to complete the blank, hydrogen peroxide, H2O2, onto solid manganese dioxide, right? So the remaining things are water and, yes, what should be the remaining thing? Next one. Yes, what is remaining here other than water? It produces only water and oxygen, Pute. Right? We know that oxygen released to the atmosphere. Right? If we do not close the test tube or the vessel that we use to prepare the gas, then water remain there, and also what? Manganese dioxide is remain there, Pute. Manganese dioxide is remain there because manganese dioxide is a catalyst here, right? Catalysts are participating for the reactions, right? But they remain in the same mass after the reaction, right? Only they are doing is they increase the rate of the reaction, right? So here the water and manganese dioxide is remain, right? Then look at the second row. Adding of dilute, blank is there, acid onto the metal, and the metal is not given, right? And the remnants given, aqueous solution of zinc chloride, right? If zinc chloride remain after the reaction, the metal should be what, Pute? Zinc, right? At the beginning of the reaction, zinc should be there to form zinc chloride after the reaction, right? So the metal should be zinc, right? So here, the aqueous solution is zinc chloride, So in acid, chlorine should be there, right? So addition of dilute, what should be the acid? Hydrochloric acid, right? Hydrochloric acid. Then inserting, yes, HCl, and the metal should be zinc, right? Inserting a burning splinter, right? When we insert a burning splinter, right? What is the observation here, Pute? It goes off with giving a pop sound, and the gas they have given, hydrogen gas. So only we have to write the observation here, right? Look at the third one. Addition of dilute sulfuric acid, right? Addition of dilute sulfuric acid onto, there's a blank, right? Then the remaining things given, magnesium sulfate and water, right? Magnesium sulfate and water, right? So water is there, Pute, right? Right, water is there. They have given the gas is carbon dioxide. So water is there, carbon dioxide is there, and this one, right? This one is given, that is magnesium sulfate, Pute, right? The salt is given, that is magnesium sulfate, So to form magnesium sulfate here, there should be a magnesium resource here, right? There should be a carbonate, right? To form carbon dioxide, there should be a carbonate, right? And it should be a carbonate of magnesium, right? Otherwise, magnesium cannot remain here, no, right? So it should be what, Pute? Magnesium carbonate. It should be magnesium carbonate, right? And it form magnesium sulfate, right? Magnesium sulfate. So in the acid, sulfate should be there, right? It cannot be hydrochloric acid. If it is hydrochloric acid, magnesium chloride should be there, right? Did you understand? So the sulfate radical should be there in the acid. So what should be the acid, Pute? Then that should be H2SO4, sulfuric acid, right? Sulfuric acid. So how we can complete the blank? Yes, addition of dilute sulfuric acid onto what? Magnesium carbonate, onto magnesium carbonate. The reaction between magnesium carbonate and sulfuric acid, Pute. Then it forms magnesium sulfate, water, and carbon dioxide gas, right? So to test to identify the gas, yes, using colorless lime water, right? Using colorless lime water, then the observation colorless lime water turns into milky, right? Then we can confirm that is carbon dioxide gas, right? Now look at this one. This is the question from 2019 paper, right? There are some other questions also right here. Now, sample of hydrogen gas by using hydrochloric acid and zinc metal, Pute, right? The reaction is given. They use from the Thistle funnel hydrochloric acid, and in the conical flask zinc granules are there, right? Write down two defects of the setup. Write down two defects of the setup. Yes, what are the defects in the setup here? Yes, there are some wrong arrangements in the setup. Yes, here, right? We use Thistle funnel to add the hydrochloric acid, right? So the Thistle funnel should be dipped here, right? The Thistle funnel should be dipped in the hydrochloric acid, right? So we have to correct that one, right? And here the hydrogen gas is produced. So the delivery tube, right? It cannot be like this. The delivery tube cannot be keep like this, because we know that hydrogen gas is less denser than air. So very easily it goes up, right? So we cannot collect it. So that the delivery tube should be there with closer to the gas jar, closer to the bottom of the gas jar, right? That is how we have to correct the setup. Right? If the gas jar is like this, right? The delivery tube should be up to the bottom level of the gas jar, right? Otherwise, we cannot collect the hydrogen gas, right? So you have to correct those two mistakes in the experimental setup, right? Then suggest two ways to increase the rate of reaction take place in the flask. Yes, two ways that we can increase the reaction rate. Yes, here they use zinc granules, right? We can use zinc in powder form, or we can use small pieces of zinc granules. Then we can increase the reaction rate, right? And also here, as the reactants, we use what? Hydrochloric acid and zinc, Pute, right? So we can use zinc in small pieces or in the powder form, right? Normally as in the small pieces, right? Here, the Thistle funnel, using the Thistle funnel, we put hydrochloric acid, no, right? So we can use concentrated hydrochloric acid, right? We can use concentrated hydrochloric acid, right? So we can, by using those two methods, we can increase the rate of the reaction, right? Mention a test to verify the gas produced is hydrogen with the observation made during the test. Yes, the same thing we can use or we can introduce a burning splinter. Burning splinter, if it goes off with a pop sound, we can confirm the gas produced here is hydrogen gas, right? So the normal method we use to identify the hydrogen gas, right? Here also you can write that one. Then we'll move to the next part, Pute, right? That is about the rate of a reaction, right? Rate of a reaction. Rate of a reaction or the reaction rate, right? First we go through the theory part, right? Then then it is very easy to write the answers. Just rate of a reaction. That is also a very important part in the chemistry section, right? Rate of a reaction or reaction rate, right? Reaction rate, right? We know that when a chemical reaction is going on, right? When a chemical reaction is going on, right? The things or the components, or we can say the substances that participate for the reaction, we name as reactants. Reactants, right? The substances that participate for the reaction, right? And the substances that form, we name as, yes, products. Reactants and products, right? So if there is a chemical reaction is going on, we can measure the rate of the reaction. We can measure the rate of a reaction, right? But here, Pute, you have to remember there is no instrument to measure the reaction rate, right? So we have to use otherwise the reactants or the products that form, right? So to calculate the reaction rate or to give to take an idea about the reaction, we use the reactants or the products, right? Reaction rate, right? There are two methods that we can calculate the reaction rate, right? One is we can measure the reactants that formed in a unit time, or we can measure the amount of reactants that used for the reaction, right, in a given time, or we can measure the amount of products that form within a given time, right? By using one of those two methods, we can calculate the reaction rate, right? Amount of reactants used. And we have to get the rate, we have to divide this by the time, right? Or one of these two, right? We can use one, right? Or right, amount of products formed, and we have to divide this by the time, right? So using one of these two methods, Pute, we can calculate the reaction rate, right? And the other thing is, right, for the reaction rate, right, there are four factors affect for the reaction rate. This is how we can calculate the reaction rate, right? And here also, we think that when we use this method, Pute, right, we get the amount of reactants used for the reaction, and we have to measure the time, right? When we use this method, we have to constant one of these two, right? That means like this, Pute, right? We confirm a time first, right? Think that within 1 minute. That means 1 minute is the constant time, constant factor, right? Within 1 minute, we calculate or we measure what is the amount of reactants used. Maybe in grams, if it is a solid one, if it is a liquid one, in milliliters, like that, right? So the time is constant there, Pute, and we calculate or we measure the amount of reactants used, right? That is one method. And the other method is we keep the amount of reactants constant and we have to measure the time, right? Think like this. We use, right, to use 2 milligrams of zinc, right? 2 milligrams of zinc. When we consider this one, Pute, right? Think the reaction is this one, the reaction between zinc and hydrochloric acid, right? Zinc and hydrochloric acid. These are the reactants, no, right? So here we use like this, right? One is we keep the time constant and we measure the amount of reactants used, right? We can take zinc in milligrams and HCl in milliliters, right? Then the time is constant and we measure these two. Then we can calculate the reaction rate, right? And the other one is, Pute, we keep the amount of reactants constant, right? 1 milligram of zinc and we can say 2 milliliters of HCl acid, right? To use these two, right? We get the reaction between, we put 1 milligram of zinc and 2 milliliters of HCl. Now the reaction is going on. These two constant, we are not adding furthermore, but we measure the time, Pute. Using a stopwatch, we measure the time, right? There, the reactants are constant and we measure the time. Or we can keep the time constant and we can measure the amount of reactants that used during that time period, right? Then here also same, right? So we can use one of those two methods to calculate the reaction rate, and there also we have to keep one factor constant and we measure the other one, right? Then we can substitute the values and get an answer for the reaction rate, Pute, right? So that is how we can calculate the reaction rate, right? Then the factors that affect for the reactions, right? I told you there are 4 factors, Pute, right? There are 4 factors affect to the reaction, right? What are the 4 factors? I think that you can remember, right? Surface area. Yes, surface area of the reactants, right? What is the second one? Temperature, right? Temperature, right? And the other one, third one, concentration. Concentration. If the reactants are in the gaseous form, right? For the gases, no concentration is there, it affects the pressure, right? It is important for the gases, right? Pressure. And the other one, Pute, as I told you, catalyst, right? Those are the 4 factors that affect for the, yes, rate of a reaction, Pute, right? Rate of a reaction, right? Now we are going to learn about these 4, right? These questions are regarding for these 4 factors, right? Surface area, right? Surface area, that is related with the reactants, Pute, reactants, right? If the surface area is more, right? If the surface area is more, that means, right, it can contact with the other reactants more, right? To form the products, Pute, to form the products, there should be a contact between the reactants. If there are 2 reactants, right, those 2 reactants should, yes, should touch with each other. Or we can say there should be collisions with the reactants to form the product, right? Otherwise, they cannot form the products, Pute, right? So there should be collisions between the reactants, right? If the surface area is more, that means more collisions are there, right? More collisions are there. So the more reactions going on, right? Then the reaction rate become high, right? So if the surface area is more collisions occur, right? Then the reaction rate is high, right? I will write in short form, right? If the surface area is high, that means more collisions, right? If there are more collisions, what happens? Rate becomes high or rate increases there, right? Then the next one, temperature, Pute, right? If the temperature is high, we know that all these particles, all are chemicals, no, right? They have a certain vibration or they have a certain kinetic energy, right? All those particles in compounds or in elements, right? Those atoms have a kinetic energy, right? When we heat them, what happens? That kinetic energy increases, Pute, right? The kinetic energy of the atoms of the reactants, right? Atoms of the reactants, when we heat the reactants, right? The kinetic energy of the reactants increases, right? If the kinetic energy increases, right, they face more collisions, right? Because they move here and there. If the kinetic energy is more, Pute, right? So what happens, right? If we increase the temperature, step by step you have to explain, right? If you have the reasons, if you ask the reasons, right? If the temperature increases, what happens? The kinetic energy of the reactant particle increases, right? If the kinetic energy increases, what happens? The number of collisions increases. Then the same thing happens, Pute. When there are more collisions, what happens? The rate increases, right? So here also what happens here? If the temperature increases, yes, kinetic energy increases, right? Kinetic energy increases, Pute, right? Then what happens? Collisions increases, right? The number of collisions increases so that the rate increases, right? That is how we write step by step, right? By giving reasons, we have to confirm our answer, Pute, right? Then very easily we can collect marks, right? Then the concentration, right? Concentration. This is mostly related with the liquid reactants, right? Concentration increases. Here also what happens? When the concentration increases, Pute, right? The number of atoms in a unit volume increases. If the concentration is more, right? Think like this, right? When we take a HCl sample, Pute, right? This is a dilute one, right? This is a dilute sample and this is a concentrated sample, right? Dilute sample means, Pute, there are more water particles, right? There are more water particles, right? I will color the water particles here, right? Water particles are there and these are HCl, right? These are HCl, right? More water particles are there, right? But the reactants is HCl, right? But in the concentrated one, there are more HCl particles, right? There are more HCl particles, only some water, right? So the number of atoms or the number of particles in a unit volume is more if the concentration is high, right? If the concentration is high, the number of particles, right? The number of reactant particles in a unit volume is high, Pute, right? So if there are more particles, more reactants in a unit volume, right? The number of collisions again increases, Pute, right? If there are more reactants, right? Because they're very close to each other now, then there are more collisions. Then again, what happens? Rate increases, right? So if the concentration increases, right? If the concentration increases, right? Reactants in the unit volume increases. Reactants in the unit volume increases, Pute. So the collisions increases. So the collisions increases so that the rate increases, right? So that the rate increases, right? So that is how the surface, and the opposite also same, right? Surface area, temperature, concentration, right? When these factors increases, how the rate of a reaction increase, right? Then the last one, Pute, the effect of catalyst, right? Catalyst is a substance that we use to increase the rate of a reaction, right? Whether the catalysts are participating, right? Whether the catalysts are participating, right? After the reaction, they remain same, right? Only they increase the reaction of the rate, right? Increase the rate of the reaction, right? Right? So the chemical composition of the catalyst does not change during the reaction. The chemical composition, only there may be a physical change, right? Physical state can be changed, right? When we put large pieces of the catalyst, right, after the reaction, right, they can exist as small pieces or in the powder form like that, but the mass is same, chemical composition is same, Pute, right? Only there may be a state change. The physical state can be changed, only that, right? So that is about the catalyst. You have to remember, catalyst increase the rate of a reaction, right? There are some substances, they decrease the rate of a reaction. We name them as what? Inhibitors. Don't mix these two, right? Inhibitors. Catalyst, only they increase the rate of a reaction, right? Directly we can say it, definitely. Catalyst increase the rate of a reaction, right? If some substances decrease the rate, they are called inhibitors. Only one example given in the book, Pute, inhibitors, right? You have to go through these things. Huh? Then we will move to the question, right? Look at effect of surface area on the rate of a reaction, right? Two test tubes are given. Test tube 1, marble chips are there, marble. Instead of calcium carbonate, here you are given marbles, right? And the test tube 2, the marbles are in the powdered form, Pute, right? In the first one, as chips. In the second one, powdered form, right? Then what happens? In which test tube does calcium carbonate disappear first, right? The reaction between calcium carbonate and HCl is going there, right? So, in which one? Test tube 2, Pute, yes. In test tube 2, right? Calcium carbonate disappear first because there calcium carbonate is in the powdered form. Powdered form means, yes, it has a more surface area, then very easily it reacts with HCl, right? Then explain the reason for quick disappearance of calcium carbonate in tube you mentioned above, right? We gave the answer as 2 years, right? So we have to give the reasons, Pute, right? We have to give the reasons, right? You can explain it like this, right? You can explain it in the powdered form one. Yes, if we take the marbles in the powdered form, that means, yes, the surface area is more, right? Surface area is more, so there are more collisions, so the reaction rate is high, right? Reaction rate is high. Like that, step by step, you have to answer, right? What is the conclusion that you arrive with above observation? Yes, what is the conclusion? If the surface area is more, the reaction rate is high. If the surface area increases, the reaction rate also increases, right? Then you have to write a practical application, right? You can write those things. Look at the second one, Pute. Effect of temperature on rate of reaction. Effect of temperature. Here we use the reaction between potassium permanganate and iron nails, right? You know the color of potassium permanganate. Yes, it is purple in color, right? We take 2 potassium permanganate solutions, right? Acidified one, because the reaction is going on only in a acidic medium, Pute, right? So we have to put few drops of acid to the potassium permanganate solution, right? Then we have to put an iron nail in equal size to the two test tubes, and right, one is in 30 Celsius and the other one is 80 Celsius, right? To make one solution, we can use boiled water, right? Write down the observation. Yes, what we can observe. Yes, the test tube in 80 Celsius, right? In the test tube in 80 Celsius, the color of potassium permanganate, or you can write purple color, disappear first. Purple color disappear first in the test tube in the temperature of 80 Celsius, right? What is the conclusion that you arrive? What is the conclusion here, Pute? Right? If the temperature is high, that means the kinetic energy of the reactants also high, right? If the kinetic energy is high, yes, that means that there are more collisions between the reactants. So the rate increases. So the reaction rate increases. That is how with the temperature, it increases the reaction rate, right? Write down two instances, right? That you use this one in daily life, right? You can write the answer, right? Yeah, hurry to the third one, effect of concentration, Pute. Effect of concentration, the third one. Write down the observations. Here, there are 3 test tubes. The reaction between magnesium and HCl. In the first one, it used only 2.5 milliliters of HCl. In the second one, 5 milliliters. Right, in the third one as 10 milliliters, Pute. Right, in the third one, write it as, in the third one means C. Right, in test tube C. Right, test tube C, write as 10 HCl. Then write down the observation. The reaction between magnesium and HCl, Pute. What happens there? It forms magnesium chloride and hydrogen gas. So in the test tube C, we can observe, yes, in the test tube C, yes, we can observe gas bubbles are evolving fast, right? Gas bubbles means hydrogen gas produced here. Gas bubbles are evolving fast, right? Thank you, right? Evolving fast in test tube C, because there are 10 milliliters in the test tube C, right? So that is the observation. What is the conclusion, Pute? Right? So we have to write the answer regarding to the concentration. Regarding to the concentration. Right? So if the concentration is high, Pute, in a unit volume, there are more reactants. There are more reactants in a unit volume. So the number of collisions increases, so that the rate of the reaction increases, right? That is how we write when the concentration increases, how it affects to the reaction rate, right? Now, then the third one, effect of catalyst on rate of reaction. Effect of catalyst. Here you are given the table that is given in your textbook, Pute, right? You have to remember these 4 reactions, the chemical industries and the catalysts that used in those industries. Production of ammonia in Haber process. Haber process, yes, it used porous iron as a catalyst. Porous iron, right? In the production of sulfuric acid, yes, what is the catalyst used there? Vanadium pentoxide, V2O5, right? V2O5. I write here V2O5, vanadium pentoxide, right? For the third one, production of nitric acid, platinum, right? Platinum used as a catalyst, right? Platinum. And production of margarine by using unsaturated fat, yes, nickel is used as a catalyst, right? Nickel is used as a catalyst, right? So that is about catalyst. I told you they increase the rate of the reaction, right? If any substance decrease the reaction rate, they are called inhibitors. Inhibitors. And you have to remember these 4 industrial methods that use the catalyst, right? Then a question from 2021 paper, right? That is not only about the reaction rate, right? It is regarding with the metals and their reactivity and all those things, right? Normally, you are not given the questions from lesson by lesson. You know that one, no? Right? It is a combination of the lessons, right? Look at this, Pute. The table given below shows chemical properties of copper and the metals X and Y, right? We don't know what are X and Y. X and Y are not the standard symbols, right? And we have given some hints, right? Copper. Reaction with water, no reaction, right? Copper does not react with water. And with dilute hydrochloric acid, no reaction, right? That is about copper. And the other 2 metals, X, right? Rapidly react with cold water. Rapidly react with cold water. And reaction with dilute hydrochloric acid, Pute, it is a vigorous reaction, right? Very, very fast. Then why? No reaction with cold water, but rapidly react with hot water. No reaction with cold water, but rapidly react with hot water. There's a hint there, right? And reaction with dilute hydrochloric acid, very rapid reaction, right? So according to this given information, we have to guess what is X and what is Y, right? No reaction with cold water. Why? No reaction with cold water, but rapidly react with hot water, right? 4x, rapidly react with cold water, right? So we know, right? If a metal react very rapidly with cold water, yes, it should be sodium, right? It should be sodium. We know when we put a very small piece of sodium into water, it gives that sound and it can burn also, right? It floats over the water surface, right? And magnesium does not react with cold water but very rapidly react with hot water, right? So X is sodium and Y is, yes, magnesium, Pute, right? Y is magnesium, right? Use the above symbols where necessary and answer the questions given below. You have to use the given symbols. You have to use the given symbols. Yes, X is sodium, right? Write down the above metals in the descending order of their reactivity. Yes, in the descending order of their reactivity. Yes, what is the answer, Pute? Descending order. So what is the most reactive one? Yes, descending order, no? Then most reactive one is first. So X should be there. They asked to use the given symbols, right? So you cannot write as sodium, right? So X is there, first X, right? This is 2021 question, right? Part 1, descending order. X is there, then Y, then copper, right? X, Y, copper. It is necessary to insert hydrogen in the series you mentioned above, right? Between which metals you mention in 1. Here, above, should hydrogen be inserted? If we want to insert hydrogen here, right? If we want to insert hydrogen here, between which metals you put hydrogen? Between which metals you insert hydrogen? Yes, in between what, Pute? This is about the activity series, right? I will explain it later. So we have to put hydrogen here between Y and copper. Hydrogen is there, Y and copper. Between Y and copper, we have to put hydrogen, right? Third one, mention the metals in the table given above which are relevant for the statements mentioned below. A is given, stored in kerosene oil, kerosene or paraffin in order to prevent it coming in contact with water. Yes, what is that metal, Pute? Yes, what is the metal that we store in paraffin oil or kerosene oil? Yes, it should be sodium. So the metal is X. Right, normally we keep all the other metals like magnesium, aluminium, zinc, copper, all the other metals, yes, that is exposed to air, right? They also tarnish, or we can say they also make that oxide layer. In magnesium, you know that one, right? Normally magnesium is a metal, so it has that metallic luster, that shiny surface luster, right? But when we expose magnesium to air, right, it forms that magnesium oxide layer, right? So when we take magnesium for the reactions or for the experiments, we remove that layer by using a sandpaper or a scissor like that, right? But sodium, right, we cannot do like that. We know that sodium is a very soft metal, right? It is rapidly react with water and oxygen in the atmosphere. So to avoid that contact, we put or we immerse sodium in paraffin oil or kerosene oil, right? That is to avoid the contact with oxygen and water vapor, right, or water, right? Be extracted by reduction of oxygen of the metal. Extracted by reduction of oxide of the metal. Yes, reduction methods, right? Reduction methods. Again, I am saying it is related with the activity series, Pute, right? So it should be Y, right? Reduction methods. Yes, fourth one. Y is a bivalent metal, right? It reacts with dilute hydrochloric acid and forms its chloride and a certain gas, right? Certain gas. Write down the balanced chemical equation for this reaction, right? We have to write the balanced chemical equation. Yes. Why they are given that Y is a bivalent metal, Pute? Yes. To write the formulas, we want the valency, right? We want the valency because we have to use the given symbols, right? So so here Y is a bivalent metal. It reacts with HCl. HCl. Then it forms the chloride of Y and it is a bivalent metal. The valence is 2, Pute. So it should be YCl2 plus what? Hydrogen gas. YCl2. So to balance the equation, we have to put 2 here. They asked to write the balanced chemical equation, right? So this is the answer for the fourth one, right? Then up to the from the ninth one, Pute, preparation of standard solution from that one, that is regarding with the grade 11 chemistry, right? So we will stop for that, right? We will keep that one until we come to the grade 11 chemistry part, right? Then I have to explain some other factors regarding with the grade 10 chemistry part. Then we can totally cover the grade 10 chemistry part, Pute, right? Then next day we can move to the the physics part, right? Look at this one, right? So we discuss about the reaction rate, right? We discuss about the reaction rate, and because of that we discuss here, right? I will explain some factors regarding the activity series, Pute, right? Activity series. Now we know the periodic table and all the elements in the periodic table, right? In the periodic table, right, metals are there, non-metals are there, gases are there, like that, right? But here in the activity series, only the metals are there, right? In the activity series. right? Activity series, right? How we prepare the activity series is Pute, according to the descending order of the reactivity, right? According to the descending order of the reactivity. Descending order of the reactivity, right? We arrange the metals in the activity series, right? Here the reactivity means Pute, how they react with water, how they react with acids, how they react with oxygen gas, like that, right? All the reactions are given in the textbook, right? We will do some questions regarding those part, right? So the metals have arranged according to the descending order, right? Then we name that series or that arrangement as the activity series, right? I think you can remember the activity series, right? Within 2 seconds, write the activity series as you remember, right? I know that you know some songs also regarding this one. Yes, right. This is the descending order of the metals, right? Descending order, right? From top to bottom, right? Reactivity, from top to bottom, reactivity decreases, right? Reactivity decreases. Pute. Rest, what are the metals? Potassium, sodium, calcium, magnesium, aluminium, zinc, ferrous, tin, lead, copper, mercury, silver, platinum, gold, right? Silver, platinum, gold. Then why hydrogen is there? Right? We know that hydrogen is not a metal, right? I told you in the activity series only the metals are there, right? Then why hydrogen is here? That is only for the comparison, right? We use hydrogen only for the comparison, right? It is not a metal, right? Only for the comparison we use hydrogen, right? So don't misunderstand it. We use hydrogen only for the comparison. Normally we say just below hydrogen or just above hydrogen, like that, right? That is why we use hydrogen here, but right, anyway, only the metals are there in the activity series, right? So top to bottom, right? Top to bottom, the reactivity decreases, right? Reactivity decreases, right? First one, there are some factors that you have to remember regarding these metals, Pute, right? Mostly the metals in the top of the activity series, right? Mostly the metals in the top of the activity series, they exist mostly as chlorides, right? Mostly as chlorides in marine water, right? So, right, we need this arrangement or this uh, series to find or to determine the extraction method of these metals, right? We know that these metals we cannot find as pure metals, right? There are some, but most of the metals we cannot find as pure metals, right? In soil or in marine water or anywhere, whatever they are, right? So they exist as compounds, Pute, right? They combine with other metals and they form compounds. So we have to extract the pure metals, right, by those compounds. So we have to select a method to extract those metals, right? So it depends on the reactivity of those metals, right? So the metals at the top of the activity series, right? The metals at the top of the activity series, Pute, right? The extraction method is what? The electrolysis, right? Electrolysis, I am writing here. Electrolysis of fused or molten chloride. Fused or molten chloride. That is the extraction method of the metals at the top of the activity series, Pute. Right? I told you most probably they exist as chloride in marine water. Right? So the method we used is electrolysis of fused or the molten chloride. What do you mean by fused or molten? Fused, that means directly we convert the solid into liquid, Pute, by heating, right? Without dissolving it water, right? When we dissolve something in water, that is a aqueous solution, aqueous. But here we use the fused or molten solution, right? Fused or molten solution, we use the method electrolysis, right? So this method we learn in grade 11, Pute, right? Electrolysis of sodium chloride we learned there, right? I think that you know now, right? And the metals in the middle, right? The metals in the middle of the activity series. Metals in the middle of the activity series, most probably they exist as oxides or carbonates. Oxides or carbonates, right? So we use reduction methods. We use reduction methods to extract them, right? Reduction methods. In grade 10, we learn about the iron extraction, right? Iron extraction in the blast furnace, we learned that one, right? So there we use the reduction methods, right? And the metals at the bottom, right? The metals at the bottom of the activity series, right? That means that according to this series, their reactivity is very low, Pute, right? Their reactivity is very low. So normally they exist as pure metals, right? They exist as pure metals, right? That is why gold and copper and those things, right? Those metals are used in the ancient times, not like as sodium or potassium, right? So because to extract sodium and potassium, it is very difficult, right? Because they do not exist as pure metals, right? There's a question like this, right? And when we consider copper or gold, they exist as pure metals, only they mix with sand or gravel or soil like that, right? So by using very simple physical methods, we can remove them or we can extract them, right? By physical methods, by using physical methods, we can extract the pure metals, right? By using physical methods, right? No need to use special methods like this, right? By only using physical methods, we can get the pure metals of these, the metals at the bottom of the activity series, right? So those are the things that you have to remember, Pute, and you have to remember how they react with oxygen gas, how they react with acids, right? The metals at the top and in the middle and at the bottom, right? Normally, you know, these metals, they do not react with oxygen gas. That is why we use gold and silver for making jewelry, right? They do not lose their that metallic luster, right? They have the shiny surface when they exposed to the air, right? So by using physical methods, we can extract the metals at the bottom of the activity series, right? So you have to remember these things regarding the activity series. But Pute, go through the reactions of these metals. right? It is given in the book. Go through the reactions and you have to remember. And for the given reactions, right? For the given reactions, right? You have to write the balanced chemical equations, right? Practice that one also, right? As I told you, we will do some questions regarding this one, right? So that is about the activity series, right? That is about the activity series, right? And there is another one that I have to mention, right? Another part in the chemistry section, that is about the chemical changes, right? Chemical changes, right? So in the chemistry part, we learn about the changes in matter, right? Changes in matter, right? You know, here matter means the three physical states, Pute, right? So these changes that occur in matter, right, we can categorize into two, right? In grade 8 also you learn these things, Pute, right? As the physical changes, yes, physical changes and chemical changes. Physical changes and chemical changes, right? I think you can remember the difference between the physical changes and chemical changes, right? In the physical changes, only the physical state is changed, right? There is no change in the chemical composition. We can get the substances after the reaction without any chemical change, right? Only there may be a state change, right? As the very simple example, boiling water, right? It is only a physical change, right? Liquid water converts to water vapor, right? Like that, Pute, right? In the physical changes, only the physical state is changed. There is no change in the chemical composition, right? The chemical changes, right? In the chemical changes, chemical composition is changed, right? After the reaction, right? The we cannot observe the things that participate for the reaction, right? New substances are formed, right? New substances are formed after the chemical changes, right? There, there may be a physical change and also definitely there is a chemical change, right? So you have to remember some examples for these two also, as I mentioned, right? Boiling water for the physical changes, right? For this one, rusting of iron, burning a cracker, burning firewood. But burning means a chemical change, right? Burning anything, right? That means that substance react with oxygen gas, Pute, burning, right? So those are chemical changes, right? Then, right? When there is a chemical change is going on, we cannot observe how the atoms or the atoms of the reactants behave, right? We cannot see with the naked eye, no, right? But we can give some evidences, right? There are some observations that we can confirm, right? That we can confirm the chemical change is going on. Yes, the chemical change is going on. What are those evidences, Pute? Yes, to confirm that a chemical change is going on, what are the evidences we can prove that one? Yes, there may be color changes, right? There may be color changes, right? Evolving of gases, right? Evolving of gases and temperature changes. Changes means the increases or decreases, right? There may be temperature changes, evolving of gases, color changes, making of what? Precipitations. Yes, making of precipitations, right? Giving orders, right? Giving flames, right? Like that, there are some evidences that can prove a chemical change is going on, right? So according to these observations, we can confirm a chemical change is going on, right? So you have to remember these observations, right? Or the evidences that we can prove, right? Then there is another thing, Pute, that I have to tell you, right? When we consider the chemical reactions, right? Chemical reactions or the chemical changes, I told you the substances that participate for the reaction we name as reactants, and the newly made substances after the reaction we name as products, right? Reactants and products, right? So according to the chemical reactions, right, according to the way that the reaction is going on, right, there are, yes, there are 4 types of reactions. There are 4 types of reactions. I think that you can remember, Pute, right? Yes, chemical, yes, chemical combination reactions. Now you can say chemical combinations, chemical decompositions, chemical decompositions. The third one, single displacement. Single displacement. The fourth one, double displacement. Yes, right. So those are the 4 types of reactions, Pute. Chemical combinations, chemical decompositions, single displacement, and double displacement, right? So according to the way that the reaction is going on, right, those reactions can be categorized into these 4, right? I will write one example for one. Chemical combination. That means 2 or more reactants combine and form new products, right? And form new products. The very simple example I will take, the reaction between magnesium and oxygen, or we can say burning of magnesium in air. I told you burning means react with the oxygen gas, right? And it forms, yes, magnesium oxide, Pute, right? And the thing, we have to write the balanced chemical equation. Here, magnesium, one magnesium in this side also, right? Here, 2 oxygen, only 1 oxygen is there, right? So can we erase this one to balance the equation? No, Pute, right? Or can we put 2 here? No, then it is wrong, the formula for magnesium oxide, right? I told you, only we can put whole numbers in front of the compound or the element, right? So we have to write 2 here. Now, 2 magnesium, 2 oxygen. 2 oxygen in this side also. Then we have to write 2 here, Bude. Right? So, burning of magnesium in air. Magnesium combine with oxygen and form a new compound. Right? So, the combination can be between elements and elements, or compounds and compounds, or like here, element and compound. Right? And it forms a new compound or more compounds, right? Here only one, right? And if you have like asked like this, Uday, right? If you are given this reaction, or in words, burning of magnesium in air, burning a piece of magnesium in air, write 2 observations. How can we write? Yes, what are the 2 observations when we burn a piece of magnesium in air? Yes, what is the color of the flame? Yes, it gives a Yes, bright white color flame. It gives a bright white color flame. And also magnesium oxide is a, yes, white color powder pute. It remains a white color powder, right? So there are two observations regarding this one, right? Regarding this reaction. There are two observations, right? So that is the chemical combination, right? Look at the next one, chemical decomposition. Chemical decomposition, right? I will write one example for that one, right? Heating calcium carbonate. Heating calcium carbonate. Yes, then it gives calcium oxide and carbon dioxide. Calcium oxide and carbon dioxide. One compound separates into other compounds or elements, right? One compound decompose, it separates, decompose into other compounds or elements, right? So the decomposition of calcium carbonate, right? As we discussed earlier, right? When we prepare, what is the gas? Oxygen gas. The decomposition of potassium permanganate, right? There also we heat potassium permanganate. So it decomposes into potassium manganate. Yes, can you remember? Manganese dioxide and oxygen gas pute, right? So that is also a chemical decomposition reaction, right? For the question, you can be asked any of these, right? So you have to remember all these things, pute, right? So this is a decomposition reaction. Now you know combination and chemical decomposition. Look at the next one, single displacement. Yes, single displacement, right? I will write one. We write this one. Right. The reaction between magnesium and copper sulfate pute. That means we put small pieces of magnesium into a copper sulfate solution. What is the color of copper sulfate? Yes. What is the color of copper sulfate? Blue color, right? That luminous blue color pute, right? So when we put some pieces of magnesium into copper sulfate solution, here also you can get an observation, right? What happens here is, right? What happens here is this magnesium, right? Single displacement. This magnesium or copper displaced by magnesium. Copper displaced by magnesium. Then magnesium combined with sulfate. Magnesium combined with sulfate and copper get displaced, right? So the products are what? Magnesium sulfate, and copper remain. Or we can say the copper deposit at the bottom of the test tube or the beaker, right? This like this way, pute. We get a copper sulfate solution, right? We get a copper sulfate solution. It is in blue color, no? Right? Blue color, right? And what happens, right? We put small pieces of magnesium to that, right? We put some magnesium pieces into that, the copper sulfate solution, right? Magnesium. Then what happens, right? Copper sulfate has this blue color because of copper pute, right? Because of copper. Then what happens? When magnesium displaces copper from copper sulfate, right? Then magnesium combine with sulfate and form magnesium sulfate. There is no color for magnesium sulfate, right? So what happens? One observation here is the blue color disappears gradually, not at once, right? When you write the answers, right, you have to write it very clearly, pute, right? So the blue color, right, blue color of copper sulfate disappears gradually, right, when we put magnesium into a copper sulfate solution. And we can observe copper deposit at the bottom. What is the color of copper, pute? Brown. Yes. For the observations, we cannot say copper deposit at the bottom, right? We can say brown color powder remain at the bottom. Yes, brown color powder remain or deposit at the bottom. Right, there are two observations, Pute. The color of copper sulfate disappears gradually and a brown color powder, right, brown color powder deposit at the bottom. Right, so single displacement. Copper is displaced by magnesium, single displacement. And you have to remember, now you know the activity series, Pute, right? This happens according to the reactivity of metals. Reactivity of metals, right? Now we know magnesium is more reactive than copper, right? Magnesium is more reactive than copper. So magnesium can displace copper, right? Magnesium can displace copper because magnesium is more reactive than copper, right? Only a metal, right? Only a metal with a more reactivity than copper can displace copper by the copper sulfate solution, right? When we put gold here, right? When we put gold here, gold cannot displace copper because gold is less reactive than copper, right? Did you understand? So only a metal with a higher reactivity than copper can displace copper from a copper sulfate solution, right, Pute? Now, then the fourth one, double displacement reactions. Double displacement, right? We will write this example. The reaction between barium chloride and sodium sulfate, right? Here only a single displacement is there, right? But here there's a double displacement. That means the metal in this compound, right? That means here barium goes with sulfate, and the metal here, that means sodium, it combines with chlorine, double displacement. So it forms barium sulfate as the product, right? Barium sulfate and sodium combined with chloride here. So it forms sodium chloride, NaCl, right? We have to balance the equation. So I put 2 here, right? Because 2 sodium and 2 chlorine is there, right? So we have to balance the equation. So there should be 2 sodium chloride in the other side, right? Look at here, Pute. Double displacement, right? Barium, sodium displaced by barium and barium combined with sulfate, right? And then sodium combined with chloride here and form barium sulfate and sodium chloride. There also you have to write the balanced equation, right? You have to write the balanced equation. So this is about the 4 types of chemical reactions, right? 4 types of chemical reactions. If you ask to write one of these chemical reactions, right, you have to remember these equations. So if they are given a reaction and if they have asked to which type, right, to which type this reaction belongs, then you have to remember these 4, right? Chemical combinations, chemical decompositions, single displacement and double displacement, right, Pute? So those are the 4 types of chemical reactions, right? So that is about the changes in matter, right? So now, right, we have discussed not in detail one by one, right? But with the questions, we have discussed all the chemistry part, including the practicals, right? Including the practicals, Pute, right? So again, go through all the things, right? Regarding the chemistry part, right? And I told you that we will do a paper regarding all these subject matters in chemistry part, right? The next day, I hope to start the physics section, right? There are many things that we have to discuss in the physics section, that and it is very interesting. Only we have to nothing to remember. Only we have to get the theory to the mind, and only we have to do the calculations, right? So we prepared. I will send the paper before the next Sunday, right? So that is only about today, right? So I will stop the class, right? If you have any question, send me a message, Pute, right? Okay, then thank you very much. Good night, all of you.
Thank you, teacher.